students, in the prior lectures we have seen what is boundary layer thickness. Along with that we have studied what is displacement thickness, momentum thickness as well as energy thickness. Along with all these concepts we have studied what is von Karman's energy equation. Combining all this concept we will study and apply on real life problems on boundary layer theory. So we have a problem over here that states that if the velocity distribution of a laminar boundary layer on a flat plate is given as u upon u infinity, a, b, u upon delta, y upon delta, c, y upon delta the square plus dy by delta the whole cube. We have to evaluate what is value of a, b, c, d from all the boundary conditions, and boundary layer thickness, that is delta, which is a function of x, shear stress, that is tau, and coefficient of drag, which is CD. So for calculating this entire part, first we need to calculate what is value of a, b, c as well as d. To do that we have to write down the equation and we have to substitute the boundary conditions. So let us substitute the boundary conditions in this equations. So let me write down the equation, that is u upon u infinity is equals to a plus b y by delta plus c y by delta square plus d y by delta cube. So this is the entire equation. Now in this equation we have to substitute the boundary conditions to get the value of a, b, c and d. So to know the boundary condition, first let us draw a flat plate. Now from this flat plate, on this flat plate there is air which is moving at u infinity. Now during the movement of air there is a formation of boundary layer. Now when there is formation of boundary layer, this point is called as a leading edge. Here the boundary condition is x is equals to 0, y is equals to 0, u is equals to 0 and delta is equals to 0. So this is the origin point or the point of leading edge. So one boundary condition we have got. The second boundary condition is on any value of x-axis. So let us consider the point here at some value of x, y will be 0, then the second derivative of u will be 0. Now why the second derivative of u is 0? Because in this range there is some velocity gradient, but the double derivative of velocity gradient is 0. So these conditions which are on the inner side of the plate, this is called as the inner boundary condition, and the boundary condition which are on the top of this entire layer are called as the outer boundary condition. So at this point value of y will be equals to delta, u will be equals to u infinity. We know that at y is equals to delta the boundary layer will end. Once the boundary layer ends, the value of velocity will be equals to u infinity. Now over here let us take another point. Here also y is equals to delta, but beyond this, when y is equals to delta, there is no velocity gradient. Why there is no velocity gradient? Because now the velocity will be equals to the free stream velocity, hence du by dy will be equals to 0. So we have got all the four boundary conditions, two inner boundary condition, two outer boundary condition. Let us substitute in this equation and calculate the values of a, b, c and d. So if we substitute the first boundary condition, we get over here at x is equals to 0, y is equals to 0, u is equals to 0. So when we substitute this part left hand side is 0, a plus all these y values are 0, so 0 plus 0 plus 0 will get this as a equals to 0. Once we get a equals to 0, this is removed from this entire part. So our next equation becomes, after solving the constant, that is u upon u infinity is equals to by delta plus d cy by delta square plus dy by delta the whole cube. Now here let us substitute the second boundary condition. Before substituting the second boundary condition, let us write down the new equation now. So the new equation except a will be writing, so that will be u upon u infinity is equals to b y by delta plus c y by delta square plus d y by delta cube. So this is what the equation is. Now over here what we have to do, we have to substitute the second boundary condition, which states that at y is equals to 0, second derivative du by dy, d square u by dy square is equals to 0. So for that we have to first substitute over here, we have to first derivate this twice. So first let us derivate this once. So we'll get this as a du by dy is equals to u infinity into b upon delta plus c to u by to y by delta plus d 3y square by delta cube, and here it will be square. So this is the first derivative. The second derivative is d square u upon dy square into u is equals to u infinity. So now over here y term isn't there, so this will be 0 plus this will be equals to 2c delta square plus this will be 3 into 2y into d upon delta cube. So this is the value which we have got. Now we have to substitute over here value of y is equals to 0. So if y is equals to 0, this part will tend to 0 and this part will tend to 0. Hence at y is equals to 0, these two parts are 0. So over here u infinity cannot be equals to 0, delta cannot be equals to 0, hence c will be equals to 0. So we have got the value of c as 0, that means this part will tend to 0. So we have substituted the second boundary condition. Now the equation becomes, that is u upon u infinity is equals to b y by delta plus d y by delta cube. So c value has been 0. So we have substituted what are inner boundary condition. Let us substitute what are outer boundary condition for this equation. So over here the outer boundary conditions are at y is equals to delta, u is equals to u infinity. So let us substitute this over here. So this is equals to u infinity upon u infinity is equals to b into this will be equals to delta by delta plus d delta by delta the whole cube. So this will be equals to 1. So we'll get this as equation as b plus d equals to 1. So we have substituted the third boundary condition. Similarly, if we substitute the fourth boundary condition, which is at y is equals to delta, du by dy equals to 0. So we already know what is du by dy, that is from the previous section. Du by dy is equals to u infinity. Let us check this out. We have done this before. U upon u infinity, du by dy, b by delta. C value we don't have to consider, this part will be 0, and d is equals d into 3y square by delta. So let us substitute this value. So this is b by delta. There won't be c value because c value is 0, and d into 3y square by delta cube. So over here we have to substitute the value of y is equals to delta. So over here this value will be equals to delta. So once we substitute the value, we'll get this as left hand side will be equals to 0, right hand side will be u infinity into b by delta plus 3 into delta square into d upon delta cube. So this value which we have got over here, we can see that this is value of delta. Delta can be taken outside, so this is u infinity by delta is equals to b plus 3 times d. Over here these two part can never tend to 0, but this constants can be equals to 0. So the over here b plus 3d is equals to 0. We have got this as equation number 2. Previously we have got equation number 1 as b plus d equals to 1. If we solve these two equations, b plus d equals to 1, we'll get the value of b is equals to 3 by 2 and value of d is equals to minus 1 by 2. So on simultaneously solving this, so we have got the values of b and d. So once we have evaluated the values of b and d, let us substitute back in those equations. So when we'll substitute, we'll get u upon u infinity will be equals to 3 by 2 y by delta minus 1 by 2 minus 1 by 2 y upon delta the whole cube. So this is our equation. Let us name this as equation number 1. This is the boundary layer equation. So once we have got the equation, after substituting the boundary condition, let us calculate what they have asked, that is boundary layer thickness in terms of Reynolds number. So for that we have to apply what is von Karman's energy, von Karman's in momentum integral equation. So let us apply in this equation where our equation, boundary layer equation, u upon u infinity is equals to 3 by 2 y by delta minus half y by delta cube. So this is the equation which we have. Now for that we have to calculate what is the boundary layer thickness. Now for calculating the boundary layer thickness, what we need over here is, first thing, we need to apply what is von Karman's in momentum integral equation. So let us write down von Karman momentum integral equation, which is tau is equals to rho u infinity square dou theta by dou x. So this is the equation. For that, first we need what is value of theta and then we need value of tau 0. So first let us calculate what is theta. Theta is a momentum thickness. Now we know momentum thickness is given as integral 0 to delta u upon u infinity into 1 minus u upon u infinity into dy. So this is what is value of momentum thickness. Okay, so now let us substitute what is this u upon u infinity. So this is integral 0 to delta. This is 3 by 2 y by delta minus 1 by 2 y by delta the whole cube into 1 minus 3 by 2 y by delta plus 1 upon 2 y by delta the whole cube into dy. So this is what is the equation. Now to evaluate this equation, we'll take let y by delta is equals to x. So hence the equation becomes theta is equals to integral 0 to 1. We have seen this before also. Why this is 0 to 1? Because when x is equals to 0, y will be equals to 0, rather the reverse case, and when y is equals to delta, x will be equals to 1, and value of dy is equals to dx into delta. So we are substituting y in terms of x. So this equation will become now, that is 3 by 2x minus 1 upon 2x cube plus 1 minus 3 by 2x plus 1 upon 2x cube into dx into delta. So this is what the equation we have got. So therefore, the value of theta can be directly solved in the calculator. So we'll get this value of theta as 39 by 280 times delta. So we have calculated what is momentum thickness. Now that is in terms of boundary layer. And next thing, we need to calculate what is tau 0. We already know by Newton's law of viscosity, this is mu into du by dy at y is equals to 0. In the previous sections, we have calculated du by dy, which was equals to u infinity into 3 by 2 upon delta minus 1 by 2 into 3 y square upon delta cube. So this we have already calculated in the previous section, but that was in the form of b and b and d rather. But now the values we have are already calculated, so we'll just substitute these values and we'll evaluate the answer. But over here we need at y is equals to 0. Hence, this entire part will be equals to 0. So this part is 0 is equals to u infinity this part will be 0. Hence, du by dy at y is equals to 0 is equals to u infinity into 3 by 2 delta. So we have got value of du by dy. Let us substitute back in this equation. So the shear stress now becomes tau 0 is equals to mu into u infinity into 3 by 2 times delta. So we have got the shear stress and we have got the momentum thickness. We can substitute that and we can calculate what is von Karman's momentum integral equation. So we have got what is the shear stress in this equation. Now what we'll do is we'll substitute the von Karman's equation, which is equals to tau is equals to rho into u infinity square dou theta by dou x. So we'll equate these two equations. So what we'll get over here is mu into u infinity into 3 by 2 delta is equals to rho into u infinity square dou theta by dou x. So over here one value of these and this part will go away, and what will be left with over here is 3 mu 2 by delta is equals to rho u infinity. We know that value of momentum thickness, that is theta, is given as 39 by 280 times delta, which we have calculated in the previous section. So we'll substitute over here dou by dou x into 39 by upon 280 by delta. So let us substitute in this equation. So what do we get after cross multiplying? Let us take all the terms related to x on the left hand side and all the terms which is related to delta on the right hand side. So this is 3 by 2 mu into dou x upon a rho into u infinity. All the terms will be equals to dou delta into delta. We'll take this 280 upon 39 on the other side. So into. So we'll consider these part as k because this part will be what, a constant, and then we'll integrate these two parts. So on rewriting this equation, what we'll get over here is this is integral k into dou x is equals to integral dou theta into dou theta into delta. So when we integrate this, so this will be kx plus c is equals to delta square by 2. So we have got this equation. So now we know that at leading edge x is equals to 0, delta is equals to 0, c is equals to 0. So this equation will be kx is equals to delta square by 2. So after resubstituting this in the equation, what we'll get this as equals to, this will be upon rho into u infinity, and the constants will be 140 upon 13 is equals to delta square by 2. So this again will be multiplied on the other side, and this will be multiplied by x, so x term will be there. If we multiply by x in the numerator as well as in the denominator, we can see this is as rho u infinity x upon mu. This is what is the Reynolds number, and so this can be written as 140 upon 13 x square upon a Reynolds number is equals to delta square by 2. So on taking this on the other side and taking square roots, what we'll get this as delta will be equals to 4.64 times x upon the square root of rex. So this is boundary layer thickness in terms of x as well as Reynolds number. So we have got this term. Now what we have to calculate is the shear stress. Now shear stress we already know tau is equals to, which we have seen in the previous section, tau is equals to mu into u infinity into 3 by 2 times delta. So we'll use this equation and we'll substitute the value of delta which we have calculated. So this will be equals to tau is equals to mu into u infinity 3 upon 2 delta. This is the equation. So this will be mu into u infinity into 3 by 2 into 4.64 into x into square root of rex. So this tau 0 will be equals to 0.323 mu into u infinity upon x into square root of rex. So we have got what is equation of shear stress in terms of Reynolds number. Now this equation of shear stress will help us to calculate what will be the shear force or the drag force. Now we know that drag force can be written as Fd. Fd is equals to integral 0 to L tau 0 b into dx. So if we substitute the value as 0.323 into mu into u infinity upon x into square root of rex b into dx, this we have to integrate from 0 to L. Just for our convenience, we'll take this value as supposingly capital C. Need not to write this over and over again. So this will be equals to C integral 0 to L. Reynolds number is actually rho u infinity x upon mu, and this x will be over here, this is under the square root into b into dx. So this will be C, this term will go outside, so this will give us as equals to rho u infinity upon mu into integral 0 to L into x raised to 1 by 2 b into dx. So over here we can see this will be x raised to 1 by 2 because this is x root x into root x, and this value will be minus 1 by 2. So once this is minus 1 by 2, we have to integrate this. So this value will be equals to c into rho into u infinity upon mu into this is x raised to 1 by 2. So if we put the limit, this will be L raised to 1 by 2 upon 1 by 2, that will be equals to FD. So now if we put back over here in this equation, we'll get this as FD will be equals to C into square root of rho into u infinity upon L upon mu into 2. This will be the value into B. Will substitute the value of C, so force due to drag will be equals to, this will be including 2, this will be 0.646 into B into mu infinity into square root of REL. So this value we have got, that is the drag force, and coefficient of drag is given as due to drag we have calculated. So coefficient of drag is equals to force due to drag upon 1/2 rho into A into u square. So this is the formula, or u infinity. So let us substitute this. This is 0.646 into B into mu into u infinity into square root of REL upon 1/2 rho into B into L, that will be the area, into u infinity square. So over here u infinity and this infinity has gone, B and B has gone. What we will be left with over here will be these terms, that is rho B u infinity and L. As we can see, this mu upon rho infinity L and these three terms will form 1 upon the Reynolds number, that will substitute over here. So CD will be equals to 1.292 upon REL but into square root of REL. Now this can be calculated as directly 1.292 upon square root of REL, which is the Reynolds number in terms of Reynolds number, or rather coefficient of drag in terms of Reynolds number. So I hope you have understood how we have calculated the unknowns in those equations by substituting the inner boundary condition and the outer boundary condition. Then we have used von Karman's moment and integral equation to calculate what is boundary layer thickness in terms of its Reynolds number. Then we have calculated shear stress by both von Karman's equation and Newton's law of viscosity. Along with that, we have calculated the shear stress as well as force due to drag and coefficient of drag. So I hope all these concepts are clear in this problem. Thank you.